What's up, geometry? Thanks for tuning in for another episode of Math with Mullins. Today we're going to look at lesson 5.8, coordinate proofs. So we're going to be able to figure out how can we place figures in a coordinate plane and then write a coordinate proof off of what we placed. Let's go ahead and get started. A coordinate proof is a proof with geometric figures in a coordinate plane, and they use variables to represent the coordinates, so the results are true for all types of that figure. So what we're going to be looking at is how can we write those coordinate proofs and why would those work? So we're going to look at a few of those examples and try to get through some of those examples we see in our notes currently. Let's get started. First example we're going to look at is just a general idea of when you can place a figure in a coordinate plane, we want to make sure it's convenient for finding the side length. So what we're going to do is assign coordinates to each vertex, and I'm going to show you kind of how that is. It's more so like an abstract thought, not necessarily a concrete number that we're assigning. So let's start with a rectangle. When you're trying to figure out the answer to this question, you're just trying to figure out the easiest way to do that. So I always want to start it in the quadrant 1 where you have positive numbers. And let's say that the height of this can be letter K from this point all the way down to 0. Okay. And then a rectangle would have another length, and we'll call this length H. So here in the top right-hand corner would be H, comma, K, however long it is to however tall it is. And then over here we have 0, comma, K. And then down here we have this point, which would be H, comma, 0, so that it's going to create this rectangle. Now I just use these variables because what you can do is interchange these variables with different numbers. Say for instance we had 4, comma, 5 as one of the points, or 5, comma, 4. It doesn't matter as long as you understand that you're building kind of a skeleton of what this rectangle could look like with variables, okay? The next thing we talk about is with a scalene triangle. Remember, a scalene triangle has 3 different sides. So again, let's start by drawing that quadrant 1. Okay, and maybe with the scalene triangle we have 0, 0 as an option. And then we have something over here. Let's say that this is distance D, and we'll call that D, comma, 0. So from here to here is the distance of D. But then somewhere in the middle, it's going to have to be different. Maybe let's say, pretend this is like 3, comma, 2. That would need to be a totally different letters or totally different variables. So we can call those F and G. So now we notice that we have 3 separate variables, which would also represent 3 separate numbers, okay? And that's where we would need to show our reasonings and understanding of scalene triangles do not need to have matching sides. If you did this example and you actually applied numbers to it, that would be fine. So for maybe the rectangle one, you used 0, maybe we use 4, comma, 0. This one could be 4, comma, 2. And then this one could be 0, comma, 2. Okay, that's just one way you could use numbers, but I'm trying to show you can also use letters to represent any type of number. For here, maybe you used D is equal to 5, so we can say 5, comma, 0. And then here, maybe we say this is 2, comma, 3. So again, I use 3 different numbers to represent my 3 different sides. I know this one looks more like a scalene triangle, but again, if I would have plotted it correctly, it would look a little bit different. Okay. What we're going to do next is we're going to write a plan to prove that SO actually bisects angle PSR. So go ahead and look to see, here's PSR, and we're trying to make sure, is SO actually bisecting it? Now it says write a plan. That doesn't necessarily mean you have to prove it. So you're basically just trying to get a general idea of how you can use this on the coordinate plane. One thing you can do is first, maybe think about side lengths of triangle POS, funny name they chose for this one, and triangle ROS. And then you remember you can use the distance formula for those. The reason you'd want to find the side lengths of those is first you just want to see, are there any sides that are matching? Okay. once you do that, maybe you can think, could I use the side-side-side congruence theorem to show that hopefully triangle POS is congruent to triangle ROS, okay? From there, then you can maybe say corresponding sides and angles are congruent. So angle PSO is congruent to angle RSO, which means that ray SO does bisect PSR. Okay? And so that's just one way that you would want to write a plan. Again, notice we didn't write anything specifically down for the proof. We were just kind of giving a general idea for that. Okay? This next one says, place an isosceles right triangle in a coordinate plane, then find the length of the hypotenuse and the coordinates of his midpoint M. So what we're going to try to do is think about what are some ways that we can write a proof with just variables here so that it doesn't matter what type of isosceles right triangle we use, whether it's at 0, 0, or whether it starts at a different spot on the coordinate plane. We want to be able to use the same kind of system or the same formula every single time. So the first thing that would probably help is just draw a picture. And again, I'm going to set it up easy for us so that we're starting it in the first quadrant. Right isosceles triangle means two of my lines are the same and one is different. Okay, so let's pretend that this is obviously 0, 0, but this one over here could be like 0, 2. And then this one would also have to be 0, 2. So we're going to start by just representing that with a variable. So whatever number I choose here, I would also have to choose here. So 0, k and k, 0. Once we get that, we also want to make sure we want to define the length of the hypotenuse and the coordinates of his midpoint. Well, here's my right angle, so that means this is my hypotenuse. So this could be my letter M for midpoint, which would mean I need to prove that from here to here are the same. And let's maybe even name this one. We can name this triangle ABC. A, B, C. Okay. So what we can first do is use distance formula to find length of hypotenuse, which would be length AC. Okay, so we could do that by doing the change in x's squared plus the change in y squared. So that would look like this, kind of plugging those things in. Maybe I say that I have my x's, x1, y1 be here, and my x2, y2 be here. So then all I would do is I plug in these numbers to my distance formula. So I would have k minus 0 squared plus 0 minus k squared. Okay, that's going to reduce to just the square root of k squared plus k squared, which is equal to the square root of 2k squared, which if you find the square root of that, it's just going to be, when you take out the k squared square root is just k, so then I have k square root of 2. Okay, so that would be how you could find the distance of that. And then you would use the midpoint formula to find the midpoint. So the midpoint would be the averages of the x's, so 0 plus k divided by 2, and k plus 0 divided by 2, which ends up being k over 2, comma, k over 2. So really you're just finding whatever your letter k is and dividing it by 2 for your midpoint. So there's your midpoint, and then this is your distance. Okay, so the length of AC can be found by doing k times the square root of 2, and then your midpoint is found by just doing k divided by 2, and that'll give you your midpoint and your hypotenuse a little bit easier. Okay? The last little bit we have are just looking at a few different proofs. We have one here and then one more right after this. The coordinates of the vertices of quadrilateral O, T, U, and V are given to us. What we want to be able to do is to prove OTU, which is this triangle, is equal to UVO. Okay, so what we're going to do is start with our given. So maybe we'll just write this in paragraph form. So I'm going to create a text box and we're just going to go through that together. Probably not 48 point because we can see that a little bit easier if we go down just a little bit. Okay, here we go. I'm not sure why it is starting over here. One moment, please. All right, we're ready. So we are given the coordinates of vertices for quadrilateral OTUV. One thing we might want to consider next is I do see that some of these lines could be equal. For instance, UT is congruent to OV by definition of parallelogram. And maybe even before I say that, I can say UT has same slope as OV, so meaning they're parallel lines. Okay, I know that UT is congruent to OV because all I'm doing is I'm just adding plus H to letter U, where I can still start with letter M, and H is still 0, comma, or V is still at point H. V is at coordinate H, comma, 0. Next thing I can say, OU is intersecting UT and OV to make alternate interior angles. With that, those alternate interior angles being made are TUO and VOU. I know that OU is congruent to OU by the reflexive property. So then I can say that triangle OTU is congruent to triangle UVO using side angle side congruence theorem. Okay, because I've now proved that TU is equal to VO, I have alternate interior angles and then a matching side. Okay, last one, writing a coordinate proof. Again, I know the vertices of triangle NPO and NMO, and what I want to do is be able to prove that NPO is actually congruent to NMO. So let's start with that. This kind of coincides with the example we did 2 times ago. So given the coordinates of NPO and NMO, I can say PO has a distance of 2h, where MO has the same distance of 2h. So PO is congruent to MO. Then I can say maybe PN is congruent to MN using definition of the bisector, noticing that H is exactly halfway through of 2H. Okay, once I know that that's the bisector, I can then maybe say that NO is congruent to NO using reflexive property. And then now I can say that triangle NPO is congruent to triangle NMO with the side-side-side congruence theorem. Okay, that'll conclude our notes for today on lesson 5.8. You're getting a worksheet today for your homework, so tune in.